Ever stop and think about this? How does the sound of your voice, just a simple vibration in the air, get captured perfectly by your phone and turned into software? It's an incredible journey from a physical wave to pure digital code. In this explainer, we're going to dive in and follow that journey, step by step. So here's the big mystery, right? You've got this rich, smooth, continuous sound wave in the real world. And then you've got a computer, which at its core only gets two things, 1 and 0. How in the world do you bridge that gap? How does one become the other?
Well, the answer is a process called analog to digital conversion. Honestly, the best way to think of it is as a translation, moving from the language of physical waves, the language of our world, into the language of software. So let's break down how it's done.
Okay, so here's the core challenge in a nutshell. An analog signal, like the sound of my voice, is like a perfectly smooth ramp. It's continuous, with an infinite number of points along its surface. But a digital signal? That's a staircase. It's made of distinct, separate steps. The whole game here is to build a staircase that's as close a copy of that ramp as we can possibly get. And lucky for us, this whole complicated translation boils down to a pretty simple 3-step recipe. First, we're going to sample the wave, basically taking thousands of tiny snapshots every second. Then, we quantize it, which means measuring the height of each of those snapshots. And finally, we encode those measurements into the binary language of ones and zeros.
All right, let's kick things off with step 1, sampling. This is where it all begins, capturing that wave.
The easiest way to get this is to imagine you're trying to track a moving car. What would you do? You take a bunch of pictures, right? Super fast. Each one of those photos is a sample, and if you flip through them quickly, you can reconstruct the car's motion. Well, sampling is doing the exact same thing to a sound wave, measuring its height or amplitude at very specific, evenly spaced moments in time.
Okay, but how fast do we need to take these snapshots? Is there a rule? Oh, you bet there is. It's a really important one called the sampling theorem. It basically says that to accurately capture the shape of a wave, you have to sample it at least twice as fast as its highest frequency. Think about it. To really see a wave go up and down, you need to grab at least one sample near the top and one near the bottom. Anything less, and you start missing the real story.
So what happens if you break that rule? If you sample too slowly? Well, something really weird happens. You run into this problem called aliasing. And it's wild. It literally creates sounds that didn't even exist in the original recording. And I guarantee you've seen this. You know when you watch a video of a car and the wheels look like they're spinning backwards or maybe not even moving at all? That is aliasing. It's happening because the camera's frame rate, its sampling rate, is just too slow to capture the true speed of the spokes. The exact same bizarre thing happens with sound. If you undersample, you create a fake, lower frequency signal that just pollutes the recording. All right, so we've got our snapshots, a whole bunch of points in time. Now what? Well, now we have to measure how high, or what the amplitude is for each one of those points. And that brings us to our second step, quantization.
This one's actually kind of fun to think about. Imagine you're a painter, but you've only got, say, 16 colors to work with, and you have to paint this incredible, complex sunset that has millions of different shades. What do? Well, you're forced to approximate, right? For every little part of the sky, you have to pick the closest color you have in your limited set. That is exactly what quantization does. It takes the infinite possible heights of the sound wave and rounds them to a fixed number of levels.
Of course, this rounding process is never perfect. There's always going to be a tiny little difference between the real amplitude and the level you were forced to assign it to. That little imperfection has a name, quantization error. And for us, when we're listening, we hear it as a very faint hiss or noise in the background.
So how do we fight that noise and get a cleaner sound? It's actually pretty simple. We just need more levels. Let's go back to our painter. If you give them 16 colors, the painting is going to be okay. But what if you give them 256 colors, or thousands? The more colors they have, the closer their painting will be to reality. It's the exact same in audio. More levels means smaller rounding errors and a much higher fidelity sound. But, we can get even smarter about this. The basic way is what's called uniform quantization. All the steps are evenly spaced. Simple and effective. But think about something like human speech. A lot of the really important stuff, all the nuance, happens in the quieter sounds. That's where non-uniform quantization shines. It's clever. It uses tiny, precise steps for the quiet signals and bigger, coarser steps for the loud ones. You end up with much higher quality for the same amount of data. Pretty cool, right?
Okay, let's recap. We've taken our snapshots by sampling, we've measured the height of each snapshot by quantizing. We're on the home stretch now, the final stop on our journey. Encoding. This is it. This is where we finally translate everything into the ones and zeros that computers actually speak.
Now, the official name for this is pulse code modulation, or PCM for short. It sounds super technical, but I promise, the idea behind it is incredibly simple. All it does is take every single one of those quantized levels we created and give each one a unique name made of ones and zeros. We call that name a code word. So how does that actually work? Well, think of it like a license plate. Every single level needs its own unique binary license plate. The number of digits, or bits, you have determines how many unique plates you can make. So if you only have 3 bits, you can make 8 different combinations, right? From 000 all the way to 111. That means you can label 8 different levels. But what if you want much higher quality, say 256 levels? Well, then you're going to need an 8-bit name for each one, because 2 to the power of 8 gets you exactly 256 unique names. And all of this, it leads us to the big fundamental truth of this entire process. There's a trade-off. There's always a trade-off at the heart of every digital signal.
It's really simple when you boil it down. If you want a super high fidelity copy, one that's incredibly close to the original sound, you have to sample faster, and you have to use way more quantization levels. But every single one of those extra samples and extra levels costs you. It takes up space. More accuracy always means a bigger file. So you've got this choice. On one end, you can have lower fidelity, fewer samples, fewer levels, which gives you a nice, small, efficient file. On the other end, you can have super high fidelity, a crazy high sample rate, tons of levels, and you get this gorgeous, pristine sound. The catch? The file is going to be huge. And believe me, this isn't just some abstract technical concept. You make this exact trade-off every single day. Anytime you pick between low, medium, or high quality on a music streaming service, or when you're on a video call and you change the resolution settings, that's you. You are literally making a decision about sampling and quantization. You're balancing the quality you want against the data and bandwidth you have. So we've gone on this whole journey together, from a smooth, flowing analog wave to a series of digital steps. And our technology is getting so good that those steps are becoming almost microscopic, almost undetectable. But at the end of the day, a digital copy is still just an approximation. It's a copy. Which kind of leaves you with one last question to think about. As our digital copies get closer and closer to perfect, what part of that original, infinite analog soul is always forever lost in the translation?